learn like a pro.
Okay, let's dive right in. We're about to pull back the curtain on the invisible world that powers, well, pretty much everything. Electric current. In this explainer, we're going to map out what it is, how we measure it, and we'll even get into this old school mix-up. A conflict, really, that still affects how we draw circuits today.
So, to really wrap our heads around what current is, you've got to imagine you can shrink down, way down, and actually look inside a simple copper wire. And let me tell you, it's not some empty pipe. It's more like a super busy highway, just teeming with tiny, energetic particles.
All right, so check this out. Picture yourself setting up a little checkpoint on that highway inside the wire. Now, you're not trying to count every single car. That'd be impossible. Instead, you're counting groups or clumps of charge. In physics, we call a certain amount of charge a coulomb. So the real question is, how many of these coulombs are zipping past your checkpoint every second? That rate, right there, that's what we call current.
You know, it's really just like water flowing through a pipe. You'd measure that in, say, gallons per minute, right? Well, electric current is the exact same idea. Officially, it's the rate of flow of charge past a certain point. It's all about how much in how much time.
And lucky for us, the math behind it is beautifully simple. It's just I equals Q divided by T. I stands for current, which, as we'll see, is measured in amperes. Q is the amount of charge measured in those coulombs we just talked about. And T, well, that's just time, in seconds. It's the perfect recipe for figuring out a rate of flow.
Okay, so it's one thing to talk about this invisible flow, right? But how do we actually see it or, measure it in the real world? How do we make it visible?
Well, the unit we use for that is the ampere. You've probably heard of amps before, right? It's always written with a capital A. So next time you see a charger or an appliance that's rated for, say, 5 amps, you'll know that's talking about how much charge is flowing through it every second.
And here is the magic connection. It's super simple. 1 ampere is exactly 1 coulomb of charge flowing past the point in 1 second. That's it. They're basically two sides of the same coin. So when you're measuring amps, what you're really doing is counting coulombs per second.
And the tool for the job? Well, it's called an ampermeter. Makes sense, right? You literally connect it right into the circuit and it acts just like that imaginary checkpoint we talked about, giving you a live reading of the flow in amps.
All right, now this is where the story gets really, really interesting. See, for a long time, there was this huge misunderstanding about electricity that created a kind of conflict, one that, believe it or not, we're still dealing with today, every time we look at a circuit diagram.
And it all boils down to one seemingly simple question. Which way does the current actually flow? Does it go from the positive side to the negative? Or does it go the other way around?
So here you can see the two sides of the story. On one side, you have the historical model, what we call conventional current, and on the other side, you have what's really happening at the microscopic level, the physical reality, which we call electron flow.
So here's the deal. Way back when, the pioneers of electricity, think Benjamin Franklin, they had to make a guess. They guessed that it was a flow of positive charge. So naturally, it made perfect sense to them to draw arrows going from the positive terminal to the negative one. And that just stuck. It became the convention. But here's the crazy part. They guessed wrong. It's actually tiny, negatively charged electrons that do all the moving. And since opposites attract, they actually flow from the negative terminal to the positive one. So, which one do we use? You'd think we'd switch to the correct way, right? Nope. By the time scientists discovered the electron, the old positive to negative idea was already in every textbook, every formula. It was just too embedded. Changing it would have been a total nightmare. So everyone just kind of agreed to keep using the old way for our diagrams. We draw current going from plus to minus, even though we all know that the electrons are actually going the other way. It's a weird little quirk of history.
Okay, so keeping that whole historical weirdness in mind, let's actually put our formula to work. Let's solve a real-world problem and see how all of this stuff plays out in practice.
So here's the setup. Imagine we have a metal sphere, and it's got a slight positive charge. Now what that really means is that it's missing some electrons. It's got an imbalance. We then connect it to the Earth with a wire. The big question is, how long is it going to take for that sphere to get back to neutral?
And the process is super straightforward. First, we'll just figure out what we already know. Then, we'll take our formula and just rearrange it a little bit to solve for time. And finally, we'll plug in the numbers and get our answer. Okay, let's plug in our values. We know the total charge, Q, that needs to be moved is 0.0024 coulombs. And we're told that the average current, I, flowing through the wire is 0.060 amps.
So to find the time, t, we just need to divide the charge by the current.
And boom, the answer is 0.04 seconds. I mean, that is insanely fast. We're talking 400ths of a second. The whole thing happens in pretty much the blink of an eye.
So what's actually happening in that tiny fraction of a second? Well, that positive sphere is acting like a magnet for electrons. A huge stream of them rushes from the Earth, which is basically an endless supply, up the wire and onto the sphere until everything is perfectly balanced again. This is a perfect picture of that real electron flow in action.
All right, let's bring this all home. We've covered the what, the how, that weird historical mix-up, and the math. Now let's look at the standard toolkit, the actual symbols we use to design and talk about circuits.
This right here is basically the alphabet of electronics. Instead of trying to draw a realistic battery or a switch every single time, we use these simple, standardized symbols. It's a universal language, which means an engineer anywhere in the world can understand a circuit diagram no problem.
And look at this. This diagram pulls everything we've talked about together into one picture. You've got the standard symbols we just saw, you've got the ammeter right there in the circuit, measuring the flow, and most importantly, notice the arrows. There's the one for conventional current, dutifully going from plus to minus, just like the textbooks say. But then you have the other arrow, showing what's really happening, the electrons flowing in the opposite direction to get the job done. And that right there is the key takeaway. It's the mental model every engineer and physicist uses. You draw and calculate using the conventional path, but you always remember that behind the scenes, it's those tiny electrons doing all the real heavy lifting.
So we've totally mapped out the flow. But a flow doesn't just start by itself, right? Something has to give it a push. And that leads to a fantastic question to leave you with. Now that you know how current flows, what do you think voltage really is? What's the push? Think about that, and we'll catch you on the next one.